So today is the second lecture of the advanced course in classical logic. And we will consider again classical propositional logic and study two semantics for this logic, set semantics and algebraic semantics. Algebraic semantics will use Boolean algebras. And the starting question is, if we are given an inclusion, a set inclusion of this kind, is it possible to verify that this inclusion holds for all sets X, Y, and Z? Of course, it is enough to consider X, Y, and Z as subsets of some fixed set W, non-empty set W. So the question is, can we check that this inclusion holds for all X, Y, and Z? And in particular, if we want to check that this holds for all sets W, which sets are enough? Are countable sets W enough to check this inclusion? Are finite sets enough? If finite sets are enough, what is the upper bound for the cardinality? Are the sets of cardinality 10 enough for this particular inclusion? Or any other inclusion with X, Y, and Z? And so on. And more generally, is this problem algorithmically decidable? And what is its algorithmic complexity, computational complexity? In this lecture, we will answer these questions. In the first half of the lecture, we will answer these questions, and the answer is affirmative. This problem is decidable, but in exponential time. And moreover, finite sets are enough, and even singleton sets W are enough to check this inclusion. And for singleton sets W, X, Y, Z, there are only two options. X is empty or the whole set W, and similarly for Y and Z. And the algorithm will be as follows. We simply replace in these expressions the symbols intersection, union, complement with conjunction, disjunction, negation. And the inclusion symbol is replaced by implication. And then we check whether the resulting formula is a tautology. So in our particular example, we obtain this formula, and then we simply need to check whether it is a tautology. So in this lecture, we will prove why this is the case, why this inclusion holds if and only if this formula is a tautology. Okay. So this example shows that another semantics is meaningful for propositional formulas, where we assign not zeros and ones to the variables X, Y, Z, but arbitrary sets, or more specifically, arbitrary subsets of some fixed set W. So this is a meaningful semantics. And the question is, which laws are valid for these new semantics, and how this semantics is related to our previous semantics, where we assigned zeros and ones. So let us recall, we have a countable set of propositional variables, and formulas are built from variables from top and bottom, from true and false, using negation, conjunction, disjunction, implication. So this is a short description of our syntax, of our grammar. This was on the previous lecture. And the set of all formulas is denoted by the symbol FM. Okay. In the last lecture, we assigned zeros and ones to propositional variables. Now we will assign sets. So we introduce the notion of interpretation. Interpretation is a pair. W is a non-empty set. It is called a domain of this interpretation. And I is an interpretation function. It takes a variable and returns some subset of W, arbitrary subset, including empty, including the whole set W. So P of W is the set, the power set, the set of all subsets of W. Okay. Now, if we have this interpretation function, then we naturally extend it from variables to all formulas. So to the formula bottom, we always assign empty set, the empty set. To the formula true, we assign the whole set W. For negation, we use the complement. So the complement means W minus X. For conjunction, we use intersection. Disjunction corresponds to the union. And of course, these three connectives are enough. Implication can be expressed, but let us write for implication explicitly. Implication is turns into this expression, complement of A or B. Like in the usual logic, implication means not A or B. If in this interpretation the value of this formula A is exactly the whole set W, then we say that this formula A is true in this interpretation. And we write this symbol. A is true in I, under the interpretation I. A simple remark. If the value of A is included in the value of B, this means, it's an easy exercise, that this expression is equal to W. But this expression is exactly the value of implication. And if the value of implication is exactly W, this means, by our definition, that A implies B is true under I. So the inclusion between sets that correspond to A and B, corresponds to the truth of the implication. So this is what we saw on the first slide. We turn inclusion into the implication, and vice versa. Okay. So if we fix some set W and fix the interpretation function, then every formula has its value. Its value is, again, a subset of W. Now, if we always obtain W for any set W and any interpretation function I, then we say that the formula A is valid in the set semantics, or set valid for short. And similarly, I will add this set word to all notions. For example, let us introduce the notation. If A is valid, we will write like this with symbol S. Without symbol S means that A is a tautology. It is true under all valuations with zeros and ones. So here we have a new notion of validity, and our question will be how this new notion of validity related to our previous notion of validity. Again, a formula is satisfiable in set semantics, or set satisfiable, if it is non-empty for some interpretation I. So here, the value of A is the whole set W, and here the value of A is non-empty. And this is, again, these two notions are related like in our previous semantics. A is valid in this semantics if and only if not A is not satisfiable. A trivial exercise. If A is valid, then not A is always empty. Therefore, not A is not satisfiable, set satisfiable. Okay, like in the usual semantics, let us extend our notions to sets of formulas. here we had notions for formulas, now for sets of formulas. If gamma is a set of formulas, we say that it is true under I if all formulas are true in this interpretation I, like in the usual semantics. And this notion is again like in the usual semantics. A set gamma, set implies the formula A. In symbols we will write like this. If for every interpretation in which gamma is true, A is also true. So the only change is in this notion A is true and gamma is true. The rest of the definition is exactly the same. And the corresponding notion of satisfiability. A set of formulas gamma is satisfiable. And here there are some special things. If there is an interpretation, there is an element that belongs to all the values of all formulas from gamma. Here we can't simply say that there is an interpretation such that the value of every formula is the whole set W, because we want this notion and this notion to correspond to each other like this. Gamma implies A if and only if gamma with not A is not satisfiable in this semantics. And this definition of satisfiability exactly corresponds to this statement. In fact, for the case of classical propositional logic, for this lecture, we could say that gamma is set satisfiable if there is an interpretation such that the value of every formula is exactly W. For classical propositional logic, this is equivalent. This is an exercise, an easy exercise to show. But if we generalize our logic, if we consider model logic or intuitionistic logic or any other logics, then this definition is a right way to generalize the notion of satisfiability with this one element E. So one element must belong to all formulas B, to the value of all formulas B. And in fact, the explanation is simple. For example, if we want to prove this fact too, from right to left, assume that gamma does not imply A in the set semantics. So let us look at this definition. This means that there is an interpretation for which gamma is true and A is not true. What does it mean? A is not true. This means that its value is not the whole set W. So there is an element that belongs to the complement. So E belongs to the value of not A. And since gamma is true, this element E automatically belongs to the value of all formulas from gamma. So here we have the element E belongs to all formulas from gamma and to the formula not A. So gamma with not A is satisfiable. Is satisfiable. So exactly according to this definition. So this element naturally arises when we consider this notion and when this notion does not hold. So gamma does not imply A. Okay, so this is an easy exercise, and to prove this equivalence in the opposite direction is again an easy exercise. I will not do this here. Now, the answer to our question, this new semantics is exactly equivalent to our previous semantics. For any formula and for any set of formulas, gamma. First statement, A is provable from our axioms. Recall that we had, on the previous lecture, we had axioms and rules. About 10 or 11 axioms, and they're all modus ponens. And we already know the completeness theorem. A is provable in this calculus if and only if A is valid. A is a tautology. So this equivalence is already known. The new thing is in this second equivalence. So A is provable if and only if A is valid, if and only if A is set valid. More generally, the same holds if we take an arbitrary set gamma. From gamma, we can prove the formula A or derive the formula A in the classical propositional calculus. If and only if gamma implies A in the usual semantics, where we have only 0 and 1. If and only if gamma set implies, so where we have not zeros and ones, but arbitrary sets, subsets of W. And the final statement, gamma is satisfiable in the usual semantics with zeros and ones, if and only if gamma is set satisfiable in our new semantics. So clearly, so as I said, this probability and consequence relation are already equivalent according to our usual completeness theorem. So we will not prove this. We already know this from the standard course on classical logic. Furthermore, the item 2 follows from item 1 follows from item 2. Just simply take gamma, the empty set. So so we need to only to prove item 2. Moreover, item 3 implies item 2. Because we know for our standard semantics, gamma implies A if and only if gamma with not A is not satisfiable. And similarly for our new semantics. So if we want to prove some statement 2 about consequence relation, we simply reduce them to the notion of satisfiability and prove that satisfiability notions are equivalent. So 3 is enough to prove all our theorem. So it remains to prove 3. So we will prove the following theorem, which is in fact a very simple theorem with a short proof. So any set gamma is satisfiable if and only if gamma is set satisfiable. So this is the only thing we need to prove. And this will solve all our problems, including the question from the first slide. So from left to right, assume gamma is satisfiable. This means that we have the evaluation with zeros and ones. It assigns zeros and ones to variables such that the value of every formula from gamma is 1. We need to show that gamma is set satisfiable. So we need to find some set and some interpretation. Which set should we take? The answer is a singleton set is enough. We simply take some one element set. Let us call it its element E. And this will be enough. We only need to define this interpretation function I. And we define it naturally. For every variable, we define it as follows. Our element E will belong to the value of the variable P if and only if the value of P is 1. So this is a complete definition, because if E belongs to the value of something, then this means that this value is exactly the whole set W. We don't have any other elements. Okay, so we defined this interpretation I for variables like this, and then it turns out that the same equivalence holds for all formulas. So the element E belongs to I of A, which means that I of A is exactly the whole set W, the whole set, the element E. If and only if its value was 1 in our evaluation. Of course, the proof is by induction on the formula A, a very trivial induction. So if we consider conjunction A and B, its value is 1 if and only if the value of A is 1 and the value of B is 1. And E belongs to the interpretation of A and B. So interpretation of A, intersection interpretation of B, if and only if E belongs to the first one and the second one. And similarly for disjunction, for negation, for implication, and so on. So trivial induction, so everyone can do it easily. Okay, what do we have? What is the consequence of this lemma? So recall that for our set gamma, what do we knew? Its value, the value of every formula is 1. Then, by this lemma, the element E belongs to I of B. So the element E belongs to the value of every formula from gamma. By definition, this means that gamma is set satisfiable. We have found one element in all formulas B, in the value of all formulas B. Okay, so quite a simple proof. And we can observe here what was the crucial thing. So if we have a one element set, a singleton set, then the value of every formula has only two values. It can be either empty or the whole set W. W is the singleton set. So this is exactly the same as the two-valued semantics where we have 0 and 1. And this is exactly what this lemma says. So if the value is 1, then the element belongs to our set. If the value is 0, then the element does not belong to the set. And so the value of A is empty. So zeros and ones correspond to the set W and empty. Okay, the converse inclusion, the converse implication. Again, very easy. So now we assume that gamma is set satisfiable. So there is an interpretation where we have a non-empty set W, an interpretation function I, and an element, one element that belongs to the value of all formulas from gamma. This time we need to build evaluation. So we need to assign to variables zeros and ones. How can we do this? The answer is just use our previous slide, but swap these two statements. So we put that the value of P is 1 if and only if the element E belongs to the value of P. So in our set W, there are many elements, but we have in our assumption, we have one element E that belongs to all formulas from gamma. And so this element E may belong to the value of some variables and do not belong to some other values of other variables. So here we use this fixed element E. And we do not need to look at any other elements from W. We ignore any other elements from W. Again, a simple lemma with a simple proof by induction that this equivalence holds not only for formulas, but for any, not only for variables, but for any formulas. And therefore, in our assumption, the element E belongs to the value of B for all formulas. So the value of B is 1. So the value of the whole set gamma is 1. So gamma is satisfiable. So again, the proof is simple, and the trick was that we look at this particular element E and assign zeros and ones according to the membership of this element E in our sets, the values of P. So we don't need any other elements in our interpretation. So this theorem, the theorem we have just proved, allows us to conclude that the classical propositional logic is not only the logic of connectives and, or, not, but it is also the logic that describes the behavior of intersection, union, complement, and inclusion between sets, and equalities between sets, of course, because equality is inclusion in both directions. So the classical propositional logic is the logic of sets with Boolean operations. So this is the first conclusion from our lecture. Let us now go to the second semantics of our lecture, a Boolean and algebraic semantics. So we need some algebras, some sets with operations. They are called Boolean algebras. So a Boolean algebra is a set D, non-empty set D, with fixed elements 0 and 1. We do not insist that they are different. They may be the same. Usually, of course, usually they are different, but sometimes we need to consider Boolean algebras with just one element, so 0 and 1 will be the same. Anyway, so we have a set D, we have elements 0 and 1. We have two binary operations on them. We denote them like conjunction disjunction, but some authors in some textbooks, they denote them as multiplication and plus, or use some other notation like intersection, union, or square intersection, square union symbol, and so on. So we have two operations, so two binary operations, and one unary operation from D to D. And they must satisfy quite a long list of laws, of identities. Both conjunction and disjunction must be commutative, associative, and we have the distributivity law in both directions. So or is distributive over and is distributive over all. So these two connectives are idempotent connectives. A and A is A, or A is A. We also have this absorption law. По-русски как это будет? Закон поглощения. Absorption. And there are some laws that connect as element and its complement. So the intersection is empty, the union is 1, and the double complement is exactly the same as A. The Morgan laws, and some laws about 0 and 1. Of course, this list is not an independent list of properties. Some are derivable from others. For example, the last line perhaps is derivable from the previous ones, from the Morgan laws and the complement laws. And some other lines are needed. Of course, distributivity, we also need distributivity and so on. But for simplicity, let us write all laws like this. Anyway, these laws are enough to define the notion of a Boolean algebra. Moreover, in this Boolean algebra, we have an analog of negation, of conjunction and disjunction, but don't have implication. We can simply introduce implication. It will be So this is a typo. It is a binary relation. It is a binary function from D times D to D, like conjunction, like disjunction. It's a binary connective. A implies B means not A or B, as usually. Okay. So we have objects, so algebraic objects of this kind. Simple examples are if we take the set of all subsets of some set W and consider the operations of intersection, union, complement. Empty set stands for 0, the whole set W stands for 1. Then this is a Boolean algebra. One can simply check that all the properties are satisfied. More generally, this is indeed more generally. If we take not all subsets of W, but some of them. So a non-empty so S is some family of subsets closed under intersection, union, and complement. So if two sets X and Y are in our family S, then the intersection is in S, the union is in S, and the complement of X is in S. Then, of course, the empty set is in S because it is X intersection, the complement of X. And the W is in S. Then, this family of sets, S, with the usual operations, is again a Boolean algebra. Algebras of this kind are called set algebras. So example A was a special case of set algebra, but here we had all subsets of W, and here we have only some of them. But of course, closed under 3 Boolean operations. Later in this course, we will prove that any Boolean algebra, finite or infinite, is isomorphic to an algebra of the form B. So B covers all kinds of Boolean algebras. All other algebras are isomorphic to these ones. And finite Boolean algebras are isomorphic even to the Boolean algebra, to some Boolean algebra of the form A. So it is isomorphic to an algebra of all subsets of some finite set W, of course, finite. Therefore, finite Boolean algebras may have the cardinality only 2 to the power n for some n. We don't have Boolean algebras of size 20 or 100. We only have powers of 2. But for infinite Boolean algebras, this statement is not the case. Not every Boolean algebra, every infinite Boolean algebra is isomorphic to a Boolean algebra of the form A. Here is a well-known example. Consider all subsets of the set of natural numbers that are finite or cofinite. Cofinite means that the complement of X is finite. So either X has finitely many elements, or the complement of X has finitely many elements. One can easily show that this family of sets is closed under union complement. The union of finite sets is finite. The union of a finite and cofinite set is cofinite, and so on. So we always obtain either finite or cofinite subsets. So this is a Boolean algebra by our example B. But how many elements, how many sets are in this family? So how many sets, how many one-element sets are there? There are countably many. How many two-element sets? Again, countably many, and so on. How many sets whose complement is one element. Again, found countably many. And so this family has countably many sets. And therefore, this Boolean algebra cannot be isomorphic to a Boolean algebra of the form A, because in the case of A, if W is finite, then this Boolean algebra is finite. If W is infinite, so W is at least countable, then the Boolean algebra is at least has at least the cardinality continuum. So it is either finite or at least continuum. And here we have countable, a countable Boolean algebra. There are many important examples of countable Boolean algebras. And here, this is just one of the simplest examples. Okay, so these are algebras that we consider. And so these algebras are generalizations of just algebras of all subsets. Okay, but now we need to interpret the logic. In the logic, we have variables. What do we assign to variables? So the interpretation will assign to every variable an element of the Boolean algebra D, of the Boolean algebra, the element of D. And then we extend this interpretation to all formulas, again, by simple rules. To false, we assign the element 0 from our algebra. To true, we assign the element 1. The negation corresponds to the complement. The conjunction corresponds to this operation in our algebra. It is denoted by the same symbol, but of course, this is a different thing. This is a connective, and this is an operation on this set D. And similarly for other connectives. So every formula has its value. Its value is an element of D. Not a subset, but an element. And now again, some list of standard notions. So if the value of this formula A is the element 1, in fact, one can see that 1 is the greatest element in this algebra. One can simply naturally introduce some order, a partial order in the Boolean algebra, and then prove that 1 is the greatest element of the Boolean algebra. So if the value of A is the greatest element, then we will write that the symbol and say that A is true under this value, this interpretation I, in this Boolean algebra B. And so we see that this algebraic semantics generalizes two semantics we already considered, the two-valued semantics with zeros and ones. Because if D consists of simply the two elements 0 and 1, then and these operations and or not are the usual ones, like in the Boolean, in the two-valued semantics, then we exactly obtain the two-valued semantics. So this interpretation function is just the same as the valuation, the usual valuation. And this algebraic semantics generalizes the set semantics, because if D is the set of all subsets with the usual operations intersection, union, complement, empty, and W, then our semantics becomes exactly the set semantics. And so the interpretation of every variable will be the subset of W, because it is the element of 2 to the power W. So this semantics generalizes the set semantics, and set semantics generalizes two-valued semantics, in fact. Okay. And now again, a list of standard notions. A formula is valid if it is always 1 in every Boolean algebra under every interpretation. A formula is satisfiable in Boolean algebra semantics. if it is non-empty for some Boolean algebra and some interpretation I. Again, these two notions are related in the obvious way. And again, we extend these notions, the notions of, we generalize the notion of consequence to sets of formulas. So again, we write that the formula gamma, these formulas gamma are true in I if all formulas are true. And this is the standard notion. A set of formulas implies a formula A in our new semantics, in the semantics of Boolean algebras. We will introduce this symbol. If for every Boolean algebra and every interpretation, if gamma is true, then I is true. A is true. We will not introduce the notion gamma is satisfiable. We could do this, but it needs more work because we need one element that belongs to all gammas. So we need to simulate something like one element E belongs to gamma. In Boolean algebras, this corresponds to there is an element that is smaller than the value of every formula B. But we didn't introduce the notion smaller or bigger. We didn't introduce the order here. So we will skip it. And again, our main claim is that my main result is that this new semantics does not give us anything new. Exactly the same formulas are valid. And exactly the same implications from gamma implies A we have in this Boolean semantics, in this algebraic semantics, as we had in set semantics, as we had in two-valued semantics. And this is equivalent to A is provable from gamma. So only this last column is the new statement here. Everything the same, everything else is the same. And so we will prove in item, for simplicity, we will prove in item 1. So this is the first statement. A is provable if and only if A is valid in all Boolean algebras. So here I write this statement explicitly. A formula is provable in our calculus. Recall that we have a calculus, classical propositional calculus with 10 or 11 axioms and the rule modus ponens. And this is equivalent to saying that A is valid in Boolean algebras, in the algebraic semantics. The correctness from left to right, from the first to the second statement, is, of course, easier. We only need to check that all axioms are true in every Boolean algebra. This is a long but simple exercise. And that the rule of modus ponens preserves the truth. If two formulas are true, here I write if they are valid, then B is valid. But even for one particular Boolean algebra and one particular interpretation I in this Boolean algebra, this holds. If A is true under this interpretation I, and A implies B is true under I, then B is true under I. So even in this very, very special case, this is a true statement. Okay, this is again an easy exercise. I will not go into details, just one or two lines of reasoning. But the converse, to prove the converse, we will go a very different strategy. We will build one Boolean algebra and one interpretation that will do our work. Namely, if we have some formula A that is a theorem, then it is true in this particular Boolean algebra. And if A is not a theorem, is not a tautology, then this formula will not be true in this algebra under this interpretation. So we will have one counter model to all non-theorems. So the set of formulas that are true in this algebra under this interpretation will be exactly the set of all theorems of our calculus, classical propositional calculus. And this can be done by the so-called Lindenbaum algebra. And this is quite an easy thing. So recall that we have as the set of all formulas. Let us introduce the following relation on formulas. We say that A and B are equivalent if this formula A equivalent to B can be proved from our axioms using the rule of modus ponens. So if this is a theorem of our calculus, this kind of reasoning can be done for many logics, for classical logic, for classical predicate logic, modal logic, intuitionistic logic, and so on. So this is an equivalence relation. It is reflexive, transitive, and symmetric. And therefore, the set of all formulas is divided into equivalence classes. Moreover, it is not only an equivalence relation, but it is connected to, it behaves nicely with connectives. If we have two equivalent formulas and two equivalent formulas, then we build conjunction, and they are again equivalent. And similarly for disjunction. So this is a very simple property of our axioms, of our calculus. And this holds for intuitionistic logic, for predicate logic, for modal logic, and so on. This is a very common situation. So since we have an equivalence relation, we can consider equivalence classes, the set of all formulas B that are equivalent to A. And we consider the quotient set. Значит, по-русски фактор множества. Quotient set. The set of all equivalence classes. So the set of all formulas is, so we have a partition, разбиение, a partition of the set Fm into equivalence classes. So different equivalence classes do not intersect. The intersection is empty. This is a standard fact. And now the algebra, the Lindenbaum algebra, for our classical propositional calculus is the following. So we take this quotient set and introduce some special operations on them. Here are the operations. So if we have a class of A and a class of B, and we want to define this operation, we do the following. We build the formula A and B and take its class. And similarly for disjunction, for negation, for the complement. So complement of A is the class of the formula not A. 0 is the following class. Take the formula bottom, the formula false, and take its class. And similarly for the formula, for the formula true and the element 1. So this is the algebra. We also need, so I promised to build also the one special evaluation of variables. Here's the special evaluation. So if we have a variable I, variable P, then we assign to it this class. Take this variable P. A variable is a formula, so we have its class, and this class will be the value of our variable P. So this class is an element of our quotient set. Okay. I just copied the definition here. And we are almost finished. So here we define the value for every variable, but by an easy induction on the formula A, one can prove that the same holds for all formulas. For every formula, its value is exactly this class. Because if A has conjunction, then we just put conjunction inside. If we have disjunction, negation, or so the complement, these operations are put inside in the formula. So this is just a trivial statement. And what do we have now? We wanted to show that in this algebra, under this valuation, the set of true formulas coincides exactly with the set of theorems of our calculus. Let us show that this is indeed the case. So A is a theorem of our calculus, is provable, if and only if, of course, this equivalence is provable. This equivalence, so from A to top is just a tautology. It doesn't add anything. From top to A, so implication top implies A, is just equivalent to A, of course. But then, so it is provable in our calculus that A and top are equivalent. So this means that A and top are related with this equivalence relation. And this means that their classes are the same. The class of A is the same as the class of top of true, which is 1. And here, the class of A is just the value of A by our this statement. So we obtain that the value of A is 1. So exactly those formulas have the value 1 that are the theorems of our calculus. So a formula is true in our Lindenbaum algebra under this canonical interpretation, if and only if it is a theorem of our calculus. So we have proved our theorem for the first item, where we have only formula A. What about gamma? We have the second statement. This is the second statement. For every formula and every set of formulas gamma, the following are equivalent. A is provable from gamma, if and only if the formula A follows from gamma in all Boolean algebras. And the fact is that the proof is almost exactly the same. We only need to change at the very beginning. We introduce the relation A is equivalent to B modulo gamma. This means that this formula A equivalent to B is provable, not only provable from the calculus, but provable from our formulas gamma. And then we again build the Lindenbaum algebra, but with this new relation, prove all the same statements. And in particular, we will see that the formula A is true if and only if in the previous theorem we had A is provable, but here we have A is provable from gamma. So the only change is that we add gamma everywhere. Okay. Now, what are the conclusions from today's lecture? So first, now we know that the classical logic is not only the logic of zeros and ones and the connectives and or not, but it is also the logic that describes the laws of sets with the operations conjunction, disjunction, inclusion, complement, and inclusion stands for implication. And if we analyze the proof of our first part, we saw that every valuation with zeros and ones can be seen as just a singleton interpretation, because in this interpretation we have only two values, empty or the whole set, exactly like two-valued valuation. Conversely, if we have an interpretation with some set W, non-empty set, it has many elements, then every element in this interpretation behaves like a Boolean valuation, a 0-1 valuation. So if we have three element set here, then we have three independent Boolean valuations that correspond to these elements. Hence, as we said, the problem of checking inclusions between sets is decidable. Simply transform it into propositional formula and check whether it is a tautology. And the last part of our lecture is says that the same classical propositional logic is also the logic of laws that hold in all Boolean algebras. Here I say all Boolean algebras. In fact, one can prove even stronger thing. If we take some fixed Boolean algebra, but in which 0 and 1 are different elements. So we have at least two elements in Boolean algebra. So we fixed one Boolean algebra, then the classical propositional logic is exactly the logic of the laws of this one Boolean algebra. A formula is provable from our axioms if and only if it is true in one fixed Boolean algebra. We only need to require that this Boolean algebra has at least two elements, because in one element Boolean algebra, every formula is true. So this the statement will be false, of course. Okay, so this is the end of this second lecture, and we can discuss any questions if we have.